Great to see you back here, and today we're going to look at the handy trick that will help your models become more robust. Before we continue though, I wanted to quickly recap on what we did last time. And what we did is we used the backward elimination method to construct a multiple linear regression using our data. And through that method, we constructed 4 separate models. You can see them on in the background here. So model 1, 2, 3, and then 4. And when we got to model 4, we were only left with one independent variable spent on research and development because all of the other ones were eliminated. And basically, we completed the backward elimination process. However, we were left with kind of a feeling that maybe we shouldn't have excluded the last variable. And why is that? Well, first of all, we saw that this p-value is not that much bigger than the significance level that we selected. We selected a significance level of 0.05. The p-value here is 0.06, so just a bit greater than the threshold. And also when we looked at the chart, so the plot of the profit by marketing spend, we could see that even visually there is kind of a correlation here. So if you just look at the red dots and ignore the blue ones, you can see that there is kind of like a linear looking correlation here in that direction. So that kind of leaves us with a feeling maybe we shouldn't have excluded that variable. The problem here is that these methods, these stepwise regression methods, they are very arbitrary. So once you select your significance level threshold, you got to stick to it, right? We've selected 0.05, this one's 0.06, so that's greater, and we just got to cut it off and not look back anymore and just proceed with the method. So how can we improve our method of building models to assess situations like that and give, like an extra opinion or have another criteria to tell us whether or not we should have actually kept this variable? And there is a way, and we're going to talk about it right now. So let's look at this top part over here. The top part is responsible for the variable. So you have the coefficients and you've got the p-values and so on. So we've talked about it quite extensively. But now let's look at the bottom part, the second part of our report. And here, as we discussed before, we've got the stats that are for the model as a whole. So how well it's been fitted, how well it's working, and so on. So the stats that we'll be looking at today are R-squared and adjusted R-squared. And they will help us come up with a cool approach, or great approach, to improve our backward elimination method. So we already talked about both the R-squared and adjusted R-squared in the stats refresher section of this course. However, if you chose to skip that section because you're not interested in the formulas and so on, then I'll quickly recap for you now. So R-squared over here is basically a characteristic or a parameter of your model which tells you about the goodness of fit, so how well your model has been fitted. And R-squared can never be greater than 1, and you want it to be as closest to 1 as possible. The closer to 1 it is, the better your model is deemed to be fitted. However, we also discussed this part in the stats refresher. R-squared is biased, and it's biased in a way that the way it's constructed and the way these models are run, so the ordinary least squared method, it doesn't allow R-squared to ever decrease. So the more variables you add to your model, the greater R-squared will be. So basically what this means is that as long as you keep adding variables, R-squared will always grow. And we can observe that here. So if we start from the end where we have only one variable, you can see that R-squared is 0.94. Then R-squared became, well, if we go this way, it's 0.95. 0.9504, then it's 0.9507, then it's 0.9510. So as you can see, the more variables we have, the greater R-squared gets. And that's always going to be the case just because of the way R-squared is derived. And moreover, you can even include completely random variables. So if I throw into this model, I throw another variable, which is basically the temperature outside, like air temperature outside right now, then and I throw that in as an independent variable. Of course, it's not a predictor. It can't predict profit of a company that works in New York or California, but R-squared is still going to grow and is going to imply that our model is now even better fitted. So that way R squared is biased. And that's where adjusted R squared comes into play. Adjusted R squared is very similar to R squared. It's got a very similar formula, but it actually has a penalization factor. So basically, just like R squared would grow if you add more variables, adjusted R squared would also grow, but there's a penalization factor which makes it smaller, which reduces adjusted R squared as you add more variables. So there's kind of these two effects battling each other. On one hand, it's growing because of the way it's constructed. On the other hand, the penalization factor is penalizing you or penalizing the adjusted R squared and reducing it every time you add a variable. So basically, if the variable that you added doesn't make R squared grow that much, like for instance here you can see 0.9504 to 0.9507. So it only grew by a fraction, very, very small amount. Well, if that happens, then the penalization factor is going to overwhelm this growth, and therefore the adjusted R squared is actually going to decrease in that scenario. And that way we can use, and we will use, the adjusted R squared to watch the goodness of fit of our models and how it changes. So let's go ahead and do that. Let's observe the adjusted R squared in our method. What was the adjusted R squared here? It was 0.9466. Then once we excluded administration expenses, adjusted R squared went from 0.9466 to 0.9475. So as you can see here, adjusted R squared went up. We reduced, basically what that means is that the model is now better. It's fitted better. It works. These variables in this combination fit the profit variable, fit this model to explain the profit variable better than these variables in this combination to explain the profit variable, which is good. It's a good step. Okay, so that means we improved our model. Here adjusted R squared is 0.9475. Let's see what had happened to it when we move to the next step. In the next step, adjusted R squared is 0.9483. So it went up again, meaning that once again we improved our model. So altogether, these variables are doing a better job explaining profit than these variables together are doing a job explaining profit. That's great. We improved our model again. And now let's see what happens when we take out the last variable, marketing spend. So we went from adjusted R squared 0.9483 to adjusted R squared 0.9454. And what does that tell us? Adjusted R squared went down. It went down by 0.003 approximately. So that means that this model, this new model, is actually worse than this model. So this model was better fitted to predict or explain the variance in profit than this model is doing so. So there you go. So even though we excluded a variable according to our backward elimination method, this variable shouldn't have been excluded because it was improved. It was with this variable, this model is actually working better, and that is your takeaway, handy trick how to observe your models and how to create them. You don't only just follow the backward elimination or whatever method that you're using and arbitrarily follow the rules. Just instead follow the rules, but also watch the adjusted R squared and see if it's actually improving. So if it's growing, then you're doing the right thing. As soon as you see the adjusted R squared drop, then you have to stop and question, did I just do the right thing or not? And what is the trade-off of excluding a certain variable or the opposite of including the certain variable? So adjusted R squared is kind of your indicator how you're going along the way. And that's it for today. I just wanted to say that adjusted R squared is not the only model parameter. As you can see, there's quite a lot of them here. And I've already mentioned the Kaike criterion. A Kaike criterion is this one over here, and it also works in a similar way, but it's got a different calculation. We won't go into detail, but if you want to, you can look these things up a bit more and understand which one suits which of these criterions or parameters it works better in your case. For instance, a Kaike criterion, you got to find is better when it's lower. So here you can see it's big, then becomes smaller, and then goes up again. So the Kaike criterion also confirms that this model is doing a better job. So if you like have a look at the other criterions, Schwarz criterion, for instance, and see how you can maybe apply them as well. But that's it for today. Hope you find this useful and hope you'll find ways to apply this in your actual work. I look forward to seeing you next time, and until then, happy analyzing.